due to a belief in symmetry that matter could show wave-like properties. This introduced the idea of wave-particle duality in particles. He combined the photon formula, right? P equals h over lambda, with the momentum formula for a particle, P equals mv. But, a photon doesn't have any mass, and so what we need to do is we need to rearrange the formula for wavelength and then put in, instead of momentum, m times v. Now, this works only if the speed is much less than the speed of light, so v is much less than c, okay, shown right here. Lambda is the wavelength of the matter wave in meters, and h is Planck's constant. We use the 6.63 e negative 34 joules seconds. The m is the mass in kilograms, v is the speed in meters per second. Evidence for matter waves. Okay, the double slit experiment. Do you remember diffraction that we studied in the previous unit? Well, that applies here. It says prior to quantum theory, there was a clear difference between particle behavior and wave behavior. This was certainly evident in the double slit experiment. If you send large particles through two slits, like firing bullets through slits in a steel plate, then the particles would make a pattern of two vertical lines on the screen that's shown down here on the left. However, if you send a wave through two slits, like sending water waves through two slits in a barrier, then diffraction would take place and the resulting wave would form an interference pattern on the screen, as shown on the right. The bright lines would be regions of constructive interference, while the dark lines would be regions of destructive interference. Thus, particles and waves behaved in completely different ways. However, when the same experiment was done on a microscopic scale, like the quantum level, there was no such clear distinction between particle and wave behavior. When scientists fired electrons through two tiny slits, they expected to see a pattern of two vertical lines, much like the diagram above left, since like an electron behaves like a particle, so like a point charge. However, to their surprise, the electrons formed an interference pattern. This clearly indicated that electrons had wave properties, which was conclusive evidence for wave-particle duality of particles. All right, quantum mechanical model of the atom, Schrödinger, 1926. Scientists were coming to realize that in order to fully understand the atom, they had to embrace the wave-particle duality of the electron. In fact, there was growing evidence that when an electron is in an orbit around an atom, it behaves more like a wave than a particle. This proved a problem, since waves have no definite position but are spread over a much larger area. One scientist, Heisenberg, claimed that it was impossible to know the exact electron's exact location and momentum at the same time. This was called the Heisenberg uncertainty principle. It's because if you want to know where the electron is, like in orbit around an atom, a nucleus, then you need to bounce light off of it. By bouncing light off of it, you're adding energy to it. And therefore, you can know its position, but not its momentum, and vice versa. All right, so rather than placing electrons in definite orbits like Rutherford and Bohr did, right, the Bohr model we just studied in the last lesson, scientists were forced to consider the location of an electron as a probability function. So this is shown below. So notice where the cloud is least dense, there's a low probability of finding an electron, and where it's most dense, there's a high probability. This is showing the quantum state n equals 1. Okay? The region of high probability is called an orbital, and this is where we would most likely find the electron. However, there's a low probability that the electron could be somewhere else. Since we don't know the exact location of the electron or actual location, we cannot describe its path any longer. Note, these probabilities can be calculated precisely, just like exact predictions at dice or playing cards. These are not like the probabilities you would see at sporting events or for natural disasters, which are only estimates. There's a lot of uncertainty in what the outcome is going to be. The quantum mechanical model of the atom has been incredibly successful in predicting atomic behavior. In fact, its basic structure has not changed since 1930, which is amazing considering all the technological advances since then. It remains our best mathematical description of the atom to date. All right, evaluating the quantum mechanical model. You can answer all the following questions that was troubling the Bohr model. The spectra for more complex atoms with more than one electron. Why only certain orbits were allowed, why orbits were quantized. The electron now forms standing waves at these orbits. Why the orbiting electron did not emit electromagnetic radiation. Well, since they behave like waves, they no longer behave as accelerating charges. Thus, they were no longer required to emit EMR. and why some spectral lines were brighter than others. Well, certain transitions have a higher probability of happening, which is outlined clearly by the probability functions in this model. All right, we'll do some questions on the next page. Hang in there.